2 weeks ago. So maybe it's very briefly recap what we studied. That's just the toric code. Well, I'm gonna just write down the definition of the model just to, recap. These square lattice, and then qubits sitting on edges. And we had these two terms. Yes, and there are two terms, all commuting. And more importantly, we observed that there are some so-called logical operators, which looks like, well, like a string. This thing commuting with all the operators of these stabilizer generators. And there's another one which looks like this. And then, so they anti-commute, so they act non-trivially on the code word subspace. And also you can actually deform the shape of these operators by applying these stabilizer generators. And then we basically studied a bunch of properties of the toric code, such as excitations, well, logical operators, error corrections, and so on. So, so toric code is something very beautiful, but well, it's obviously something very different from trivial state, like product state. So, so in the first part of today's lecture, let's study ground state of the toric code. I mean, any one of them. How complex it is. Let's study this. And then, so, of course, what do we mean by how complex it is? So that's the, of course, the question. And then let's make this question more quantitative. Now, for this purpose, we are going to discuss the so-called circuit complexity of the toric code. But let me just give you at least one physical motivation why we should care about circuit complexity of the toric code. So toric code is, roughly speaking, it's related to what we call the topological phases of matter. But when we say phases of matter, what does it mean? So it's quantum phase. One example of phases of matter is this gas, or this air, and the other one is this solid. So in this room, like chair or desk. And then we think like they are very different, right? It's obviously different. But the reason why we can see that like they are different is because if we change the temperature of the room a little bit, of course air remains to be air, and then desk remains to be desk. So which means that these phases of matter are somewhat stable against external perturbations. That's why we can kind of interpret and understand that they are different on some phases of matter. So phases of matter is like a family of states, not like single states. And then, so for this purpose, toric code is a good candidate of a phases of matter because we have seen that toric code if we add, so this is the original toric code Hamiltonian, given these interaction terms, and then add tiny perturbation to the system. And then we have discussed that this ground state space is stable for some small but finite epsilon. Okay, Well, we made more, precise statements about ground state splitting and so on. But the point is that the properties of the ground state does not change much under the perturbations. So for this reason, given the toric code, you can go slightly away from the toric code and it still looks very different, very similar. So in this sense, toric code is like one candidate or representative of the quantum phases of matter. And the argument was basically, in order to couple different ground states, we needed to go to higher order in the perturbation theory, that is where L is this linear length of the lattice. And at Lth order, we have the term which goes like this. Well, order L, or maybe kth order, or no, mth order, whatever. And M needs to be big because V is made of very small local terms. So that's why we needed order L perturbation. But such a perturbation is exponentially suppressed and so on. So this is the argument. Okay, so toric code can be viewed as a phases of matter in some sense. But then now, next task is, of course, to show that toric code is different from something boring. And then for this purpose, the question we are going to address is so given the product state, like all zero state, and then somehow we want to create the ground state of the toric code, again, one of them. Then how difficult is it to reach the toric code ground state from zero state? And obviously there is some unitary operator, but we want to ask how complicated it is. And then we are going, so in today's lecture, we are going to show that this unitary operator is kind of very complicated in a sense that you need actually order L steps. So. Okay, so this will be the statement we are going to show. Now, but let me make this definition of steps more precise. So for this purpose, we are going to first discuss a depth of a quantum circuit. So again, with this toric code and the product state conversion in mind, let's assume that the following quantum circuit. Following means I'm just drawing a bunch of lines, but well, you can imagine some actual quantum circuit, and then so this circuit and these lines are qubits, and the time flows in this direction. And at the end of the day, you get some object, which is a toric code ground state. And then at each time step, you can, let's say, implement some 2-qubit unitary gate. And then these 2-qubit unitary gate can be, anything. Like C0 gate, Control Z gate, or single qubit rotation. It doesn't matter. So we keep applying this 2-qubit gate and then try to create the toric code. And of course, this is a one-dimensional picture, but you need to kind of imagine that there's another dimension. Now, with this picture in mind, let me define the depth more precisely. So the rule is the following. First, so gates act on neighboring qubit. In a sense that you cannot connect this qubit on this qubit, this qubit on this qubit, because there is some geometric constraint. I mean, you don't want to couple qubits which are too far away. And also, one important comment is that here we are thinking about some unitary operator which creates the toric code from the product states. But so this circuit decomposition is of course not unique. In a sense that there are many, not infinite, but I mean, there are many, many different ways to implement this actual unitary operator. So here I'm showing one particular way of implementing unitary operator, but of course there are many different ways. And even more, such that so this such an encoding circuit or preparing circuit of the toric code is also not unique, right? Again, you can think about infinite family of such unitary gate which prepares the toric code. But the point is that we would like to think about minimal steps. Okay. I mean, we want to do it as quickly as possible or as efficiently as possible. Now, I still haven't defined what it means by steps, but roughly speaking, the step is just, well, number of the time step in this circuit. So you can say like, this is step 1, maybe this is step 2, this is step 3, and then so let's say in total there are m steps, let's say. So this is the number of steps. And this number of steps is actually more in a more precise language. It is called depth of a circuit. Okay, so this is the kind of definition of the depth of the circuit. Yes?
Sorry, could you elaborate on the second bullet point that is not unique?
Not unique in a sense that, so this equation demands that if you apply unitary to 0, it brings you the toric code. But let's say if you think about other product state, and then this you could bring you to some other state, and this part is not fixed. So this equation is just doesn't give you unique unitary operator. So there are many different families of unitary operators, and some of them much easier to implement, some of them much more difficult to implement, and we are looking for the one which is most efficient. Yes?
For toric codes, what's the relationship between k and n? But when k equals 2, how many physical qubits will I need?
Sorry, k is, like toric code? Yes.
Yeah, logical qubits. So how many physical qubits do I need for the logical qubits and toric code?
How many physical qubits do you need for the...
Yeah, like if
okay.
Logical qubits, how many physical qubits do I need, or 3, etc.? Is there like some relationship?
Right. So in the toric code, in this particular construction, the total number of qubits is this, and then the code distance, which is the minimal weight, which is L, and then K is equals to 2. So these are the parameters on this particular geometry of a square lattice with periodic boundary condition or torus. But if you modify the geometry a little bit, then you can. So this is a torus in the sense that this is a, well, donut. But if you increase the number of holes, then you can actually increase the number of K, and then there are some interesting trade-off between these guys and so on. But these are a bit detailed stories. I mean, of course, it's very important. Yes, so in practice, I mean, we need to design these holes nicely so that it accommodates lots of logical qubits. Okay, so here I gave sort of a formal discussion, but all we are saying is that we want to find the most efficient way of preparing the toric code in a sense of the circuit depth. Circuit depth means that, well, basically the time step we need. Now, just to make sure, let me give you a few examples. So, let's say that I have such a circuit. So here I couple them with 2-qubit gate, 2-qubit gate, 2-qubit gate. Then what's the depth of this circuit? Then you may think like step 1, step 2, step 3. But the point is this operator and this operator, these two gates, they don't conflict with each other because they have no overlap. They are commuting. So you can implement simultaneously. Right. So in this case, we should say that this is a depth 2 circuit. But if I change the configuration of these 3 gates a little bit, namely the order we implement, like this, 1, 2, 3. Then the point is that, well, I want to bring this operator here, but this operator acts on this 3rd qubit. This operator also acts on the 3rd qubit. So they do not commute with each other in general. So for this reason, this circuit has depth 3. Okay. So as you can see, all the commuting gates can be implemented simultaneously, commuting and also non-overlapping gates. And here, of course, this is a definition of the depth of the quantum circuit. But now, what we want to do is we want to define the circuit complexity. Of a given wave function. For this, we just think about all the possible unitary operator which brings you to the target state from the product state. And then we ask, what is the minimum? So this means that we think about all the possible unitary operator which satisfies this condition, and then look at the depth, and then we take the minimum. That's the definition of the circuit complexity of the cycle. Now, one minor technical comment is that in practice, we will be fine. We will be satisfied by creating the target state approximately. In that case, you need to introduce some tolerance in these equations and so on. But in this lecture, actually what we discuss is basically stabilizer code or stabilizer state, for which we know that we can prepare exactly by using Clifford gate. So such ambiguity wouldn't be that important. But this is a minor comment. Now maybe it's nice to give you one example, that is the state or cat state, which is a superposition of a macroscopically entangled state. And of course, this is not that stable state, but it has a very interesting entanglement property. So now, the preparing circuit for this GHZ state is, I think, of course, there are many of them, but at least there is one which is very famous. That is, you start from all-zero state and apply Hadamard, and then you then implement the control NOT gate, where this is the control and keep doing it. Then the point is that after implementing Hadamard, you get and then now by controlling the result to be 1, you sort of change it to 0, 0 plus 1, 1, and keep doing it. I think this is some well-known protocol, I guess. So, I mean, if you are interested, you can check it by yourself. But the point I want to make here is that all these gates are implemented in a sequential way. So you cannot really move this gate here, and so on. So this gate has a depth is well, n, the total number of qubits. So it's a bit difficult state to create. Now, of course, this argument shows you that this particular protocol of preparing GHZ state is depth is n. But actually, in one of the I will ask you to prove that this actually n is optimal in the sense of the circuit complexity, and which is I think easy if we deal with the toric code case today. Okay. So now let's go back to the toric code and let's show that our nice, pretty toric code ground state is something very complicated. Now, for this purpose, it is important to discuss the one concept that is size of operators. So let me ask a very concrete question, that is, given a one-body operator, that's any operator, V how weak here this unitary circuit has a circuit depth m, which is some finite number. And we ask how big this UVU dagger is. Is this question clear? Now, to address this question again, I will draw a one-dimensional picture, but you can generalize this to 2 dimensions, 3 dimensions, and so on. I'm gonna draw a bunch of lines to illustrate the idea. Okay, then I'm gonna 1, 2, 3, 4. Let's make it symmetric just in case. Put this V operator here. Then I'm gonna draw a circuit diagram for this UV U dagger. Then, just for simplicity, let's say this M is just 2 for illustration purpose. Then depth to circuit would do something like this, right? So step 1, step 2, and then okay, so now let me elaborate on this figure a little bit. This part is your unitary operator. And this part is dagger. So pictorially, this UVU dagger operator, the time-evolved operator, would look like this. But now, these are not like random circuits, but it's this U and U dagger are correlated. For example, if this unitary operator, 2-qubit operator, is A, or some unitary operator, then this guy must be A dagger, right? Because it's the inverse. Again, if this is B, this will be B dagger. If this is C, this will be C dagger, and so on. Now the point is, in the unitary operators, A times A dagger is always identity. So if you look at this, okay. If you look at this whole diagram, then actually there is no point of doing this A and A dagger, because I apply A and then I cancel it. So there is no meaning of doing this. So let's just cancel this. Again, B and B dagger collide, so we can cancel this. C. Now once I cancel B and C, these guys can collide and then get annihilated. This one too. So with this in mind, the final outcome I would get is the following. So this part, I mean, I cannot push this operator to this operator because there is this V operator, which is non-trivial operator, which is not identity, so I cannot push it. This operator, because of this operator, I cannot make it collide to this guy. So from this observation, you notice that this U, V, U dagger, this time-evolved operator, looks like this. And this straight line means that this is just an identity operator. And then this UV U dagger will be 4-body operator living on this region. So by using this argument, you see that this object, how big, we have a concrete answer that is 2M body. Well, of course, in 1D geometry. And if you are in higher dimensions, maybe you have a lot of different direction to go, but the point is that it will change only this multiplicative factor. And then the point is that if M is finite, this is still a small operator, small compared to the whole system size. Now, with these observations in mind, we can show that the toric code has the order L steps or order L circuit complexity. Okay. So first observation, let's recall the following. The toric code, that object. Well, we have this string-like logical operator. Okay, the string of L. And I'm not going to draw the grid, but it's just a straight line. And then let me call this operator X bar. So this is a logical operator. On the other hand, you can also think about another string-like operator. This is also a logical operator because it commutes with all the stabilizer generators or the Hamiltonian. Okay? But at the same time, these operators are equivalent to each other in a sense that, well, they act in the same manner inside the code word space. So, and maybe more precise way to state this is X bar acting on toric code ground state. Here, toric means any ground state. This is just equals to this. So the actions are the same for all toric code ground state. Okay, so this is the statement. And I guess this is fine, right? If you want to show that they are equivalent, then you can actually use the fact that you can deform this guy to this guy by applying this stabilizer generator. Then you can slowly deform it, and eventually you can move the entire thing here. But now I can repeat the same exercise in the sense that there are other logical operators which are string-like. But now this system is very big with this length L. So I'm going to take these X bar and the X prime bar operators so that they are actually far away. So I'm going to take that they are away and order L over 2. So they're the halfway point. So they are very far apart. And so this one too. Now, one observation is that this X bar operator and the Z bar operator, they anti-commute with each other because they are like, Pauli X and Pauli Z operators for your logical qubit. But of course, the similar equation holds for essentially all the family of the equivalent logical operator. So, like this, okay? Okay, so now let me write down 3 equations. So first equation is this one. which is, I think, very trivial because x and x bar acts as in total acts as an identity on any ground state. And similarly, you have the operator with this identity. But now, let me think about the following object. This object. Now, so you apply x, z, x prime, z prime. Then they anti-commute. So meaning that if you commute x prime through z, you get -1 sign. And then you have x, x bar. So it's basically right. So this minus sign. Therefore, you have -1. Okay. These are just some trivial statements. But now we are going to use a contradiction. So suppose that order 1 depth unitary such that and then we are going to show that this leads to contradiction. Then, okay, so this equation, let's call it A. I can rewrite A in the following form. Implies right. So I just inserted this equation into A. So there's nothing fancy. Here there are two operators. U diagram X, U, and this object. And then we are going to show that these two operators have no overlap. That's kind of easy to see, I guess, because this was an X bar operator. Now, this time evolved operator would be living in this region with finite width, basically because of these observations. Each of small x operator can expand only a little bit. This means that this width will be order 1. Order 1 means that it's just the order of depth. Then you can do the same argument for x prime. And it's living here. So they don't overlap with each other. Now, with this in mind, we can show the following. Let's see. this true? I guess it's fine, right? Okay, so basically I inserted this product state here. So why is this allowed? The reason is the following. So again, this is two-dimensional system, but maybe we can just draw a one-dimensional picture. So what we are computing is like expectation value of these guys with respect to product state. So this is blur and the cat. Now I'm going to insert these two operators which have no overlap. So let's say here and here. So this is, then this is U implying. So the point is that they have no overlap with each other. Then if you look at, then this is just, I mean, this part doesn't matter, right? Because this is 0 and 0, 0 and 0. So what matters here is this part times this part. Okay. It's just a simple product of these two objects. But now in this equation, we have these two terms, first, second. Okay. So this entire object can be decomposed into just a simple product, just equals to 1. So it's almost there. Now, I always don't understand. Anyway, I think I can finish this. So we show that this product is equals to 1. But if we think about the norm of this object, then this must be smaller than 1 or equals to 1. Because, well, this x is just, oh, I need a bar, but x is just a Pauli operator, bunch of Pauli operator with eigenvalue plus minus 1. This is. So in order to multiply them together to identity, actually we need these two objects equals to plus minus 1, plus minus 1. But this implies that the this is an eigen, so product state is an eigenstate of this object. But now I think now we can easily prove the contradiction. And now I want to bring this back. Well, I can do this. So it's equation C. C implies the following, which is just straightforward rewriting of all the terms. this was -1. But so here I argued with x operator, but you can repeat the same argument for z operator. And then basically this operator is like +1 or -1. Let's assume, let's say +1 in this case, then this is +1. So I mean, it's an eigenstate, so it acts trivially on product state and you gain some phase. And then this one, let's say +1 or -1. +1 or -1. But the point is that when this is plus, this is plus, this is minus, then this is minus. So they are correlated. So this implies that this object must be equals to +1. Okay. So here is the contradiction. Therefore, the conclusion is you must be at least order L depth. And here, of course, order L comes from the fact that basically I need to fatten my string operator so that they start to overlap again. Okay. So is there any...
Why is that L over 2? Because you have two strings and if...
I just placed them...
Oh,
so this is on the torus. So,
yeah.
Right.
So, yeah. So we did L over 2.
So any questions? No? I mean, you should ask because I'm going to ask you to prove the similar statement for ZHZ state in homework. But anyway. But let me make 3 comments on this. So some comments. So first comments. We show that the depth is lower bounded by L. But the question is this lower bound optimal or not? And yes, it turns out it is optimal. And there are several different ways of preparing a toric code ground state from a product state. And I was actually planning to just give you some reference, but then last night I did some Google search and actually I couldn't find any paper which explicitly tell you how to create the toric code in order L step. So there's one method which are more heuristic in a sense that you can think about the following. Adiabatic continuation. Maybe I should say this S. Then the point is that when S is equals to 0, then this is the Hamiltonian for a product state, and then you can interpolate it into so this is what people call the adiabatic preparation. And then, well, the hand waving argument is that this model goes through a phase transition and the energy gap becomes goes like 1 over L, and therefore the time. It's actually linear interpolation wouldn't work. You need to do it very carefully, but the time scale would be L. So that's kind of the hand waving argument. And then There is a protocol which I'm aware of, and I'm not going to do it in detail, but the way it works is, so suppose that you have a torus. So I'm only going to sketch the idea. So then let's say this is open. Then this is a torus. Then suppose you have somehow created a toric code up to this point. And then basically there is a sort of a procedure. That is, you can attach this object here to make some like here, like this. Then once you have such an object, then next you can attach this kind of object. So here qubits. Then you can grow the length. And then you can do it sequentially in the sense that, so this is a time step 2t, 2t plus 1, and 2t plus 2. And then you can sequentially increase the length of this toric code lattice. So such a method exists, and I think it's pretty easy to show it. But all I want to say is that this bound is optimal. So did I lose here? Second comment is that, well, I sort of motivated all these discussions in terms of the phases of matter and so on. So very roughly speaking, when we talk about quantum phases of matter, we have several different phases of matter: phase 1, phase 2, phase 3, and they have some ground state, a gapped ground state, like toric code or ferromagnet and so on. Psi 1, psi 2, psi 3, and so on. Then traditionally, we tend to think that, well, if we have some Hamiltonian H1, H2, then we try to go from H1 to H2 by somehow connecting H1 and H2, like this linear interpolation. But if they belong to the different quantum phases, then there is a phase transition where energy gap closes, and then there's some physical property of wave function behave non-analytically at the thermodynamic limit. So these are the way we used to think. But with this circuit complexity in mind, we have a more precise definition in a sense that large depth quantum circuits are necessary in order to go from one phase to one phase. Then when we need a large depth circuit, then we say that they belong to different quantum phase, and then when you don't need any large depth circuit and just local small rotation of the qubits or something are necessary, then we say that they are in the same phases. And then this, I think, classification is pretty consistent because, well, I sort of argue that there is a adiabatic interpolation, but if energy gap does not close, then order one step circuit U to do exists just by linear interpolations. So in this sense, you can turn the argument around that if these two states are separated in a sense of the circuit complexity, then you have to go through the phase transition in a sense that the energy gap must close at some point. So all these observations, I think, are very consistent. And the final comment on this subject is following. So here we have been considering a quantum circuit which can take any form as long as couplings are local, but there are some generalization. So of course there are a bunch of generalizations, but one physically interesting generalization which people have been discussing in the last 5 to 10 years, 5 years I think, is that we want to think about unitary operator which is symmetric. So what does it mean by symmetric? Symmetric means that the system for some reason has some imposed symmetry. And one example is that you can think about system of n qubit. And then for some reason, the system has the following symmetry. It's a tensor product of Pauli X operator. So this is a rule you impose. This is a symmetry. So how we should think about is that in this system, all the unitary operators you implement should commute with this symmetry operator. Even more, when you implement such gate like this, so then let's say this is 1, 2, 3, 4. So this U12 or U23 and so on. All these operators should commute with this imposed symmetry. That is how you can think about the symmetry imposed in this system. And well, why we are doing this is that actually there are physical systems in actual condensed matter systems which have this kind of symmetries. And then there are some classifications we can do. And so one important thing is that here we have classified phases of matter by using circuit complexity. But let's say this psi1 and the phi1, well, they belong to the same quantum phases of matter in a sense of circuit complexity. But it is possible that by assuming that actually the circuit I can use must be symmetric, then there are some cases that these two phases become different. Okay. And then I don't want to use too much code, so that's fine. And I will just mention one very important example of such a phases matter, which is called symmetry protected topological phase. Which is often called SPT phase. So SPT phase is an idea of classifying quantum phases of matter in the presence of these symmetries. And one, I guess, a prototypical example of this symmetry is phases of matter is that, well, plus is 0 plus 1 state. So the eigenstate of X operator. So this is of course trivial, and symmetric because this is an eigenstate of the symmetry operator and has a +1 eigenvalue. So this is like a representative of the trivial phase. And then now it turns out in one spatial dimension, you have to consider a system which is bipartite and need to think about a pair of symmetry operator S1 and S2. So S1 acts on the odd side and S2 acts on the even side. Then it turns out, I'm going to just state the famous result. That is the so-called cluster state, which we use for the measurement-based quantum computation. This is a non-trivial SPT wave function. Under S1, S2 symmetry. Okay. As you probably know that you can create a cluster state pretty easily by implementing control Z gate. So without any symmetry, this is a trivial state. But by imposing this global symmetry, S1 times S2, it turns out cluster state. There is no way of creating cluster state from this trivial state. So even such a simple state we know from quantum information theory can be viewed as a very simple example of phases matter which people actually care, which is kind of nice, I guess. Okay, so yes.
I was just wondering for the third point, the generalization. So you were trying to show that psi1 and phi1, they're symmetry protected topological phase difference, right? Inherently, they share the same underlying quantum topological phase, but because we give the symmetry, there's encounters two different phases, and these can be related by still OL circuit or O1 circuit.
Right, so now it depends on what kind of circuit you are looking at. If you don't assume anything about circuit, just generic circuit with local neighboring 2-qubit gate, then they are just the same in a sense that there is order 1 circuit, order 1 depth circuit. But now if you impose extra symmetry, such as this bunch of X operator need to commute, and then suddenly there is no low depth circuit to connect these two states.
Okay.
And one example is this cluster state. I'm sort of assuming that people know cluster state, but cluster state is something. So you start from all these plus state, you prepare a bunch of plus state, and then for all the neighboring qubits, you implement control Z phase, and then it creates some short range entangled state, which are called cluster state, and then just by performing local measurement, you can do quantum computation. That's the idea of measurement-based quantum computation. So the way we create the cluster state, of course, it's a short-range entangled state. So in a sense of circuit complexity we have been discussing, they must be in the same phases of model. But now suddenly if I say that, okay, actually the gates I can implement must commute with these two operators, then suddenly there is no way of moving from one state to the other state. And one way of seeing it is this: actually the control Z gate does not commute with these operators. Because control Z gate is like, you have like two-body Z operators. They don't commute with X, and so it's a prohibited operation in this symmetry protected phases of matter. And then, so these kind of things have been attracting lots of attentions in condensed matter physics community. Okay. Any other question? Yes.
So in the grand scheme of things, the topological code, this is topological insulator.
Oh yeah.
The topological insulator, you can't implement toric code or surface codes on these because it doesn't have the underlying quantum phase transition.
Sorry. I couldn't follow the question.
So SPT is topological insulator, right? So we're saying in topological insulators we can't use our normal code on topological insulators because of the fact that our operators don't follow symmetry. So we need an actual topological properties materials with actual topological phases.
In order to use it as a quantum code. Yes, right. I mean, it's of course pretty difficult to find actual material with actual topological order. That's why I think we are relaxing a little bit and, just think about symmetry protected topological phases matter. Then it's, as you said, topological insulator is one example. There are more family of.
But we can't use topological insulator to do universal quantum computing, though, right?
Sure.
Okay.
I mean, it depends on the scheme. So here, when I say quantum error correcting code, I'm assuming all kinds of errors could happen to my system. But when I say that there is a symmetry in my system, somehow I'm assuming that my noises and errors act in the same, somehow it respects this symmetry. So the environment is not that bad. So that's the assumption. If there is no error, then of course we can do the quantum computations, right? Okay. Right. Any other questions? If not, I'm going to move to the second topic, which is about the topological color code. But any question for now? Okay. Okay, color code. So while I'm erasing the blackboard, let me talk about the motivation. So if you have the toric code, how do you do the quantum computation? And well, there are many protocols to do that, but one difficulty is that so logical operators you have. This is a string of X operator and Z operators. So if you implement X and Z strings, you can do logical X rotation and logical Z rotations. But like, what kind of computation can we do just by doing X and Z operator? I mean, XZ, yeah, of course they anti-commute, but you don't see anything interesting. So in order to do some non-trivial quantum computation, we should be able to implement other gates other than X or Z or Y, like somewhere in between X and Z, or some tiny rotations around X-axis and so on. And this is actually a very difficult problem, and but in some sense, the topological color code is a little bit better than the toric code because there are some gate operations you can do. But let me talk about the motivation a little bit more. So as I said that we want to implement something other than X and Z operations. So, right. So one possible idea is, again, this is a toric code lattice. This is my logical X operator, and this is my logical Z operator. Then maybe one possibility is add some small number here and implement such object. So with cosine theta amplitude, so this is theta, you implement this string of x, and then with this sine theta I amplitude, you do z. Then sure, this will do some logical rotations for any value of theta. But the problem of this approach is, of course, this is a superposition of a very, very non-local operator. This is L body and L body. Somehow you need to implement them in a coherent, superpositions. And this is very difficult, and in general, we need for generic value of theta, order depth quantum circuit will be necessary. By the way, this statement can be rigorously proven, but for now, I will just state it. And the problem is that if order L depth circuit is necessary, then so again the circuit will look like this thing. But suppose there is an error in this gate, then this error sort of propagate to the whole qubit. So in order to implement this theta rotations, you need a L depth circuit which could introduce a lot of errors to your system, and then this is very bad. So in this sense, we want to think about different methods. And then I guess, I don't know what Daniel taught, and I think he talked about magic state distillations and so on, so he probably have mentioned this thing. But before talking about the topological color code, let me mention that there is one interesting gate you can implement in the toric code, which is called the Hadamard shift. So this discussion is like slightly a detour, but I think it's still interesting. So we already know that in the toric code we can implement Pauli X and Pauli Z and Pauli Y operator easily by a transversal gate. So you guys learn transversal gate and so on, or? But if we have a toric code, we have these terms. Let's think about the following two-step implementation of a gate. So first, we implement the Hadamard gate. Everywhere on the system. Just to recap, Hadamard does so it exchanges X and Z operators. Then this Hadamard will of course change my vertex operator to this vertex operator, and the bracket operator to this. But now the point is, this operator, well, I draw it on a lattice and it looks like a vertex. But if I do a dual lattice, it looks like placket, right? By dual lattice, I mean the following. Okay. So for this reason, by just applying Hadamard gate, I have converted the toric code into other kind of toric code defined on a dual lattice. And if I want to go back to the original toric code, what we should do is that shift the lattice. By shifting the lattice, we mean that qubits are sitting here. And we just move it in one particular direction, a diagonal direction. Then after doing these two steps, you see that the original you are returning to the original Hamiltonian. But there is a non-trivial logical action because if you originally had the X string and the vertical string, you implement Hadamard the shift, so it becomes a Z string. So it must have some non-trivial action. So by using this Hadamard shift operation, actually you can do a little bit more than X, Y, Z operations. Of course, this method works only when this is exactly L and your lattice is defined on torus. But so it's all I want to emphasize here is like it's not like the toric code has X, Y, Z operators only, but there's one operation you can do. But probably there's nothing else exists in the toric code. And I guess this was sort of found in a paper by Xiaogang Wen in 2005 or 6, maybe. Of course, he didn't mention it in this context, but somehow this is the result. Now let me talk about the color code. Okay, but I think it's a good time to have a break, I think. So yes, why don't we have 10 minutes break and then let's resume. All right, so let's discuss the color code. And so for most of the time in the lecture, I'm going to focus on 2D color code, but actually the most important construction of the color code happens in 3 dimensions. But for 3D, actually, the drawing is so difficult. So I'm going to do the simplest realization of the color code, which is called the 15-qubit read mirror code. But in the problem set, actually, you are going to look at the other type of the small color code, which is something called the hypercube code. And for that, only with 8 qubits, actually, you can do a non-Clifford gate. It's just kind of cute example. But anyway, so let's do the 2D color code. So this color code is very similar to the toric code in spirit because, well, it's again a stabilizer code with topological order. So actually, I think I should keep this figure of the color code. So let me draw it here. So just honeycomb lattice. Okay. And so in the toric code, we placed qubits on edges, but now we just place them on the on vertices. It's pretty normal. And Hamiltonian was a stabilizers are constructed in the following way. Given a placket, well, there are many placket, but given a placket, we are going to place two terms on every placket. This is a stabilizer, and this is also the stabilizer. And let me call it as Px, stabilizer X at placket P. Then you can construct the Hamiltonian by just putting all these things. Okay, so the coordinate space is defined as a +1 subspace of these operators. And by the way, just a minor comment that is, you may think that this is also a stabilizer. Y. And yes, with one little bit of subtlety, because you actually need to add -1 sign to the entire object. And the reason is because x times z is, I think, well, -I times y. So there's I phase, and then I to the 6 is still -1. So there's such a subtlety. But here's the definition of the model. And this is a stabilizer code. Because all these operators commute with each other. And it's actually not so trivial to see that they commute with each other, but again, all you need to check is that when they are neighboring with each other, they only share two sides, so they commute. And one extra thing you need to check is that if you have a x operator and z operator on the same placket, then they share 6 sides or even number of sides, so they commute with each other. So this is the stabilizer code. And the reason why we call this object color code is because this lattice is 3 colorable. By color, I mean that we can put 3 color labels, A, B, C, or blue, green, red, or something, the following way. Okay, so the rule of the coloring is following. Different color labels on neighboring plackets. So A is, for example, surrounded by BC, 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 and then separated from A. Okay, so this is color code. Now this looks very similar to the toric code in some sense, but then why do we care such an object? And this is precisely because it has more implementable transversal logical gate. So first example is a Hadamard, which exchanges x and z nicely. But at -1 phase to y operator. So yes, obviously this Hamiltonian consists of x term and z term, which act in the same manner. So if you exchange x and z, still the Hamiltonian is the same. So if you have tensor product of the Hadamard, so this carry H is Hadamard and ordinary H is Hamiltonian. It's pretty confusing, but both starts from H. So this H Hadamard is a logical gate. And another example is the so-called S gate. S gate is a following operator. You put the I phase when the quantum state is 1. So it's a diagonal gate. So people often say that this Z gate is a square root of Z because Z is like, but this should be like this. Anyway, so S gate is again a transversal because in the case of S gate, Z remains to be invariant, and so actually I kind of forgot how it transforms. I think it was something like this. So the important point is that so if you multiply these three objects, you get I. So if you multiply all of them, you should get I. But now Y and Z are interchanged, so you should add some minus one sign so that it multiplies to identity. So minus should be here or there, but it doesn't matter much, I guess. So now the point is that if we apply S operator everywhere on the lattice, what's going to happen is that X operator will be changed to Y operator, and then Y operator will be changed to X operator. Okay. But this is actually unfortunately not the right thing to do, because we have this problem that Y operator, it must be a -1 eigenstate, not a +1 eigenstate. For this reason, there's one technical subtlety which can be taken care of by no, I think maybe I got this wrong. Does anyone know? I could probably do it.
There has to be one minus sign.
Yeah.
I don't remember if it's on the X or the Y.
So Z is a rotation around the Z-axis, rock sphere, but again, if it's I or minus I don't remember.
Yeah, yes. It could be I. So.
I mean, we could just do the multiplication otherwise.
It's x to y, y to minus x.
Sorry.
It's x to y, y to minus x.
Y to minus x. Okay. Sounds good.
It's a positive rotation on the Z-axis.
I thought there was some I sign. No?
Just one minus sign and that's it.
Okay. Really?
I don't know, at least that's what it said in the book, that like there should always be one minus sign where you
Okay, so it's pretty embarrassing, but I want to have some operation which maps x to minus y. And then I think I know the answer. That was something like this. So you alternate S and S dagger. I know that this would be the answer. Does this do the job? Yes, yes, they do the job, right? Yes, yes.
There is a factor of I.
Yes, yes.
Multiply x by
This is
s
from
and
the
s dagger on this side.
Do you think this is the case?
Again, I don't know where the plus or minus is.
But this is also consistent, so
But yeah, I reckon
it should be fine.
the eyes are dropped.
Okay, whatever. No, not whatever, but
Up plus or minus I.
so let
Never trust the lecture in the front on plus or minus i's and square roots of 2's.
okay, but let me try this, and then well, it's then right. Then yes. This is so embarrassing. Right. So S dagger transformation should do this. Then now, if I apply S dagger, S dagger, S dagger, then this will be mapped to Y, but with minus sign, because S gives me -1 sign, but S dagger gives me +1 sign, so you get -1 sign. Okay. Anyway, so the message is that there is a way, and well, it's actually a pretty important point that this works because this is a bipartite lattice, so there is some deep reason, but so all you need to do is you implement some S and S dagger in an alternating manner. And then this, where the phase appearing and so on, by using this trick, you can cancel the phase. So all you have to do is put some Clifford and it's dagger of the Clifford, and then it works. Anyway, the important point here is that this color code has a lot of symmetries. So therefore, there are many things you can do. Now, so yes, like this. Okay, that's hopefully. Yes.
2 questions. One, the S there is the S gate S, right?
Which S?
The
Oh, this S.
the one you just wrote right there.
Here?
Yeah.
So this S is a transversal logical gate.
Okay, so this is totally different from the S you were talking about on top.
Oh, you mean this S?
Yeah.
Oh, I'm sorry, they're different. Yes, right.
Second question is regarding.
So, right, S is S gate, and then this is a stabilizer. Okay, so that's a bad notation. Okay.
Second question is when we talk about dimensionality of the code. These things don't actually have to be in 1D, 2D, 3D, 4D, right? Do you mean dimensionality in the sense that each qubit is only connected to, so in 1D, connected to 2 other qubits, and in 2D, it's connected to 4 qubits, or maximum 4? Like, what distinguishes 1D from 2D to 3D?
What distinguishes 1D and 2D and 3D? Right. Many things, and but so actually, so I think no, it's a very important question. So the property of a stabilizer code crucially depends on dimensionalities, and then in 1 dimensions for local stabilizer code, actually there's no quantum codes, and so you need to be in 2 dimensions at least, and then sure in the number of direction you can go is pretty important, but well, there are many consequences you see difference, and it's actually one of the topics later in the lecture. But
Like, how would you know this one's a 2D code?
Oh, why I think this is 2D code? So when we think about 2D, 3D, and 4D, and so on with geometry, we have somehow implicitly in mind that there is a family of code. So here I'm drawing only part of it, but I can extend it to the infinity. So there is a prescription with increasing number of qubits, right? So in this case, I just extend this sheet and it becomes a sheet-like object. Sheet may have some thickness, but it's a 2D object. So,
but in terms of just like, like so when you're actually, suppose you can implement this code on quantum computer, right? That thing, how does that geometry relate to the geometry of our code? Right? Because it looks like they're just qubits, so then your qubits can range.
Sure. So if this system is very small, like, okay, looks like 2D lattice, but let's say it's like 4x4 or something, I could somehow implement it as like 1D system, like this kind of quasi one-dimensional system. I can view it. It's quasi-local. That is possible. And then when the system size is very small, I mean, it is not that possible to define what it means by 1D, 2D, 3D, 4D, and so on. So if you want to be more precise, you need to think about family of codes with increasing system size, and then you can see the difference. So
for here, this is, each qubit is connected to 3 other qubits, right?
Right.
And then in our previous torus code, it was connected to 4 other qubits. Right? Do we say like when it gets like 5 or 6, then it turns into like a 3?
No. Yes. Definition of the geometry. So again, if you gave me any geometry, so 2D toric code, I would say it's 2D because given a toric code, I have a prescription to enlarge it, and it's 2-dimensional sheet. And maybe for this family of code, I can define something more rigorously. But it's really important that you have some family of codes. If you gave me like qubit quantum code with 300 qubits, and then if you ask me it is 1D, 2D, 3D, 4D, and then strictly speaking, there is no rigorous answer to this question. I mean, of course, you can think about like, looks like 10 by 10 lattice and so on. So there is some just empirical answer, but if you want to be mathematically rigorous, we need to consider family of codes.
In the case of the toric code, you mentioned that you do a periodic identification of the site to make it as a torus. Do you do the same thing? Is there a way of doing it?
Right. So right now I haven't specified the boundaries yet, and then boundary does matter in the toric code. And then there are many interesting boundaries, but I think there are 3 cases we should focus. And then one is the boundary, so like the torus. We can just tile the torus geometry with this color code. And so let me write it down. We can consider color code on the torus. And perhaps you can think like this qubit is actually equal to this qubit, and then you can wrap around the torus. So this 2D color code on the torus, it turns out that this is just two copies of the toric code which are not interacting with each other. So in a more precise language, there is a way to short depth disentangles to toric code. So on a torus, color code is something pretty, in some sense, trivial, just 2 copies of the toric code. But with boundary, we have something interesting. And I'm going to discuss the case with some particular boundary where this, yes, so yeah, I'm going to discuss the boundaries. But for now, let's assume that this system is defined on a torus without specifying the, without not worrying much about the boundaries. Okay. Should I get here? All right, so now, one thing we probably need to do is to look at the logical operators. And then, again, I need to draw the lattice. Then unfortunately, it takes time. A, B, C, A, B, A, C, B, C, B, A, C, A, B, C, and so on. So again, logical operator needs to commute with all these operators. And then we can find it somehow easily by guessing. So the way we can construct it is actually you connect the placket with the same color. It's kind of neat, I think. Like this. And then you place, let's say, X operator. Then you can see that this commute with all the stabilizer generators because this line intersect with each placket, this hexagon, even times. So this is 2 times, 2 times, and 2 times, 2 times, 2 times. So this Z operator commutes with all these Z-type placket operators. But at the same time, you can of course replace this X operator with all Z operators. And so on. Then this is another valid logical operator. So in this sense, there are sort of 3 different string-like logical operator. And Z string, there are. Good. Now, if we have such a string operators, and then you can actually think about excitations, and then so this is, I think, brilliant. So, right, excitations. In order to create excitations, we prepare a part of string logical operator. So in this example, this string of X needs to go forever and then need to wrap around the torus in order to commute with all the terms in the Hamiltonian. But suppose we just terminate it at some point, so like this. So assume that this is terminated at this point and this point. Then this string-like X operator violate two terms, that is these Z terms here and this G term here. So there are some excitations, a pair of excitations here and here. So this is what we call anyons in the topological color code. But of course, you can repeat this similar exercise and then consider any string, like C, for example. And then if I think about string of Z's, then this anti-commute with X, which creates a pair of excitations. Okay. So this sounds like there are anyons related to these 6 anyons. I'm not going to draw these other 2, these 6 anyons. But it turns out these 6 of them are not independent from each other. To see this, we can think about the following process. And A, B, C. And let's just apply single Pauli X operator here. Now this anti-commute with this term, Z term, here and here. So it is possible to create this combination of these 3 objects from vacuum. So this combination of these 3 objects is just, redundant. So it looks like there are 3 independent and 3 anyons, but really only 2 of them are independent. So if I just look at the independent anyonic excitation in the color code, I can forget about color label C because C is redundant. I can express it in terms of A and B. No, sorry, this must be it's a mess. So there are 4 of them, like 4 generating set of anyons. And of course, you can think about like combinations of these guys. Yes?
Sorry, can you explain kind of how you get the vacuum and how there's only 2 of them that's independent?
Oh, right. Suppose that in this system you have 3 excitations, A, B, C, somewhere in the lattice. And then there is a, okay, I didn't explain this, but if you have an excitations here in this location, by using this string operator, you can move this excitation to anywhere with label A. Then if you have an excitation with these 3 labels somewhere on the lattice, you can move them together and then arrange them in the following way, and then later annihilate them together. So in this sense, they are like basically identical objects. In a sense that if you have A and B excitations, then you can sort of express C excitations too.
So if you have 3 excitations, like of A, B, and C, that's equivalent to no excitation.
Right.
Okay.
If three of them simultaneously exist.
And I was also wondering for the string,
Right.
can you always have a string that covers all of it? Like
Covers all means lattice.
this is like you link all the A's together, right?
Right.
Can you even do that?
Right. So that is doable because of this three colorable lattice, and then that's why this. So I'm drawing it in this hexagonal lattice, and obviously you can do this, right? I mean,
All the A's in one continuous.
Yes. And then this is doable for any colorable graph. And
that diagram doesn't include all the A's. He's left one out on the top row.
Okay, yeah, I see. But just I was asking whether there exists a string.
Right. So that's a pretty non-trivial statement, actually. Yeah. Yes.
Does the string need to run boundary to boundary, or can you have a closed string within the lattice?
So right. So I mean, the rule is it needs to commute with all the terms in the Hamiltonian, and it needs to commute the term in the boundaries. And then if the string is starting from the boundary, of course, we need to carefully define so that it commutes with the boundary terms. And then it turns out, depending on the way you define the boundaries, some of the string can end on the boundary, some of the string cannot end on the boundary, and so on. And there's interesting physics. And then I'm going to treat the case with the boundary later, which is, of course, related to the topic I discussed 2 weeks ago. It's about anion condensations. Yes?
One more question. You say that applying an X at the vertex intersection of A, B, and C will like annihilate all three excitations. So effectively you have two. Using the same logic, doesn't that mean that if you have like an excitation on A and one on B, you could just apply an X and only have an excitation on C?
Sorry.
Doesn't?
This?
No, the triple intersection thing to the left of that picture.
Here. Oh,
So
yes. Oh, right. Yes, is having A and B together is equivalent to having single C.
So I guess the question is like, why do we say that we have like two independent toruses instead of just one? If we could like treat the role of A and B like just coloring C.
So right. So think about the following simplest case. You have A, B, C, and then we only have 8 possibilities just for simplicity. A exists or not, B exists or not, C exists or not. 8 possibilities. And then among these 8 possibilities, there are only 4 of them are independent in the sense that if there is no excitation at all, 0, 0, 0, then I can convert it into 1, 1, 1. So they are the same. So that's what I'm saying. So if I have some local region, then so A, B, C, let's say exists with 0 or 1. Because if they exist with pair, then I can annihilate locally. So that's what we mean by independent. So maybe I could have explained better in a better way. So you have a lattice, and you pick a local region, and then I want to ask what kind of anion can exist in this local region. And then if I have even number of A's, I can annihilate it. So I only care if the number of A is even or odd. So it's a 0-1 information. For B, it's the same, 0-1 information. So 8 possibilities. But in addition to these 8 possibilities, this is actually a secretly same. So 1, 1, 1 is equivalent to 0, 0, 0. So in the local region, there are only 4 possibilities. Yeah. And then, of course, I can declare that I'm going to neglect C, because whenever I see I observe C, I convert it into a pair of A and B, for example. Then these are the generating set. In the case of the toric code, we had these 2 guys, bracket and vertices. So now, in this sense, if you double the toric code, you have another vertex and a bracket. So then the number matches. So that is actually the reason why this color code must be equivalent to 2 copies of the toric code. But of course, this is not a proof. You actually need, in order to show this, you actually need to give the such a circuit, and it's not an easy program. But this is a way of saying that the color code is secretly 2 copies of the toric code. So I often get the question that is, then why do we need to think about color code? Because it's just 2 copies of the toric code. And in some sense, it's true that the physics are the same, but the beautiful thing about color code is that these symmetries manifestly visible in a sense that if you apply Hadamard, then it exchanges these logical operators nicely and so on. So for this purpose, this reason, the color code is very practically very useful. Anyway, so this is the physics. But I have been looking at things on the bulk and without thinking about boundaries. But I think it's now nice to talk about boundaries. And now I need to draw another figure. So I think one annoying thing about color code is drawing is really annoying. So I think that's, again, the reason why usually people don't want to treat it on lectures. But I think this is a very important subject. So let me try to draw it. Okay, now I'm not so confident. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So give me 1 minute. That should be done. Okay, so let me just make it a little bit look nicer. All right. Okay, so now let me add color labels A, B, C, A, B, C. Okay, like this. So it's still three colorable. And you see that A doesn't neighbor with A, and so on. And it's actually convenient to think about some spatial infinity point. So this is just a fictitious object. So I'm drawing 3 points, but these 3 points are actually identified, so it's a single point at the spatial infinity. And then there's some big triangle here, triangle here. And then I can put some color label, just B, C, and then again, this still satisfies the colorability condition because B does not, B and B are separated. Because in this line, you have only AC, AC, AC. So this is the construction of the color graph. Then again, you put the qubits on the vertices. Now, I'm not going to put qubits on spatial infinity. This is just... Okay, so now in the previous case, I just discussed that it is equivalent to 2 copies of the toric code. And on the torus, this means that there will be 16 ground states. But with this color code on the boundary, it turns out that there's only single logical qubit. And this is a bit non-trivial statement, and I don't think it's quite relevant to quantum information purposes, how to derive k equals to 1, but maybe I can briefly derive it. So let's say this L is this lattice. And let me extend it by adding 1 point at the spatial infinity. Then this whole system is wrapped around, so this has a geometry of the sphere. Now let me use this number of vertices, edge, and face. And then you have this nice formula that is always equals to 2. So let's use this to derive that k is equals to 1. So on L, number of vertex is, of course, v minus 1, because I'm removing spatial infinity. And the number of faces is f minus 3, because I'm removing 3 faces. Now, number of total qubits n is equals to v minus 1. Okay. And the number of stabilizer generators is 2 times f minus 3, because on each face we can define the 2 stabilizer generators. So this value must be equals to k. But to find the value of k, we use this, namely this important property is that given the vertex, there are 3 edges. But this edge is shared by 2 vertices, which means that E must be, okay. So if we combine these 2 things, what we get? Right, yeah. And we just plug this into this, and k is equals to v minus plus 5, which is minus 4 plus 5 is equals to 1. So that's somehow you can see that this system has only 1 logical qubit. So it's a so 1 logical qubit, 2 ground states. Okay. Anyhow, this code has only 1 logical qubit, so it's much easier to discuss. So what are the logical operators? It's actually pretty easy to find one expression of a logical operator. It is this one. Transversal application of X and Z operators. The reason is the following. So this acts everywhere on the lattice, and you see that X and Z operator has even weight on all these faces, so they must commute with the all the stabilizer terms. And moreover, n is actually odd, which is something you can, by counting, you can convince yourself, and also you can argue this by these arguments. well, it's actually, this equation does not make any sense if v is odd number. So v must be an even number, and then v must 1 is an odd. So v is even, v must 1 is an odd, and so on. But it's just observation. The important point is that these acts like a logical X and logical Z. Okay, I think that's fine. But now, obviously, these are not the smallest expression of logical operators. But when we compute code distance and so on, we care about the smallest distance. And in order to find the expression logical operator, actually this picture of the boundaries and what kind of string operator can end on the boundary and so on is very important. So we argue that it is possible to construct a string operator by connecting faces of the same color. So let's do the same trick. So first, we connect B like this, and we can consider a string of X starting from the boundary. And then these operators commute with each other, and all the bulk operator, except this point. This implies that, well, this system is a bit small, but if we have a very big color code, you can define a string operator sort of ends at B and create single excitation. Okay. So in this sense, B boundary condenses this on NU. Okay. Then you can but do the same thing. You can think about other, let's say this is C, then you can connect C with this C, and then implement X, 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 X. And then this commutes everywhere on the lattice, all the terms, except this term. Okay. But now we know that it is possible to create, let me draw it in a bigger. Just by applying single X, it is possible to create the following set of excitations. That is on B, A, C. This is single X, 3 excitations. So now what we should do is we just need to bring this NU back to its home. This. So then this operator should commute with all the terms in the Hamiltonian. Okay, is this okay? So just to recap, the point is by constructing a string operator starting from the boundary, you can create an enum, single enum on the bulk, and that you can do from all the 3 boundaries. But now, if these 3 types of the enums come together, we can annihilate it. Now, if we write down all these process, this is just a bunch of 3 string X operator colliding at one point. And this is this must be a logical operator because it commutes with the Hamiltonian. And it's actually, you can write down this is an X type, but you can write down the Z type operator in the same manner, like this one. So the prescription is you just pick a point in the lattice and extend it into 3 directions. And the point is they collide at only a single location, so these operators anti-commute with each other. So they are the logical operators. And you see that no matter how you create this object, the distance is the weight of the operator is order L, where L is the length of the system. So this is the topological color code. Yes?
So I have a question. I thought we have, if 3 excitations come together, it's equivalent to identity, right?
Mm-hmm.
So what is that then?
Oh, so imagine that there is this operator. It's a X string, X string, X string, and then at one point. Then now, let's imagine what it does. So if I start implementing this operator from the boundary X like this, it will create an unique excitation here and then bring it to the center. And then we can later annihilate 3 of them. This is the process. So I started from the ground state of the system, created a little bit of excitation, 3 of them, and then annihilated. So I return to the ground state. So this is a logical operator.
Okay.
And then now in this argument, I draw 2 different types of logical operator. One of them is X and Z. They anti-commute with each other. This means that they are the logical operators. And they are big in the sense that you cannot really define such an object in a local manner. Any questions? Good. Okay, so this is the topological color code. There's this one, I think it's maybe I can erase this board. Now I think it's good to make some connection between this topological color code and some known code. So I guess you guys have learned 7-qubit code, I guess. Is it? Thing code? I don't know the precise name, but this code is actually the smallest realization of that color code with boundaries. And just to see that, well, it's a very small colorable lattice. 3 colors, that's it. We place qubits. So there are 7, 1, 2, 3, 4, 5, 6, 7. But I'm gonna label qubits in this particular manner. I mean, labeling doesn't matter, but this is nice to see the connection to 7-qubit code. And then we have stabilizer living on this 4-body, but so right, 1, 3, 5, 7. Okay, I'm gonna just go write it down. And same for these. These are the stabilizers with the 7-qubit code. But the point is, this is precisely the color code. 1, 3, 5, 7 is C, and then 1, 2, 5, 6 is yes, B, and then 1, 2, 3, 4 is A. So C, B, A. You can do the same thing. Okay, so now let me just mention the higher dimensional topological color code. And unfortunately, I really cannot draw 3-dimensional lattice for the color code. It's really difficult. So what I'm going to do is I'm going to discuss again something like this 7-qubit code, or it's called the 15-qubit code, which you probably have learned in the magic state distillation. But the point is this 15-qubit code admits a non-Clifford transversal logical gate. And again, you can interpret it as a 3-dimensional topological color code, also known as 3D. Now, let me try to draw a lattice. Hopefully, I succeed. So first, I draw a tetrahedra, and it's very similar, but this is there will be 15 qubits. Okay. Did I draw all of them? Hopefully, yes. Well, I think you get the message, right? Or you get the message that I don't want to draw the full lattice. This is, I mean, this is already beyond my capability. So this is the smallest example of 3-dimensional color code. Now, important point is now we have 4 colors. And then, well, in this example, there's only one of each color labels, but like A, B, C, D. But the point is that you need to think about volume object, A, B, C, D, and you need to place them in a way that they don't. They are not neighboring with each other in the same color. Yes?
Okay, related to that question, where there are internal qubits as well within that tetrahedron, right?
Right.
And where are they? I think those are the ones that maybe you forgot to draw.
I think that, right, there's one. Yes, there's one.
And it's like,
I forgot draw, and then which is right, you are right, and which is at the intersection of all these 4 volumes.
okay.
I was counting only 14 before.
Okay, that's great. Yes. Okay, and now let me make only some statement that is this 3-dimensional color code. It turns out if you define it on a torus means 3 torus, so you can consider a cubic lattice, sort of cubic geometry with opposite faces identified. Then it is equivalent to 3 copies of 3D toric code. Then I guess you can guess, right, by induction that this Lydium color code. Okay. But anyhow, this is just a statement. So now, probably you have already learned this from Daniel, but let me show that this 15-qubit code, or this 3-dimensional color code, has a transversal T-gate. And actually, so again, so this code has only one logical qubit, which is okay, but it would be nice to have another example of 3D color code with multiple qubits, and it's actually in the problem set you're going to study a version of the color code which has 3 logical qubits, and that one has some interesting transversal gate. So in this case, it's T-gate. It's a square root of I with some ambiguity in the definition. But the point is it's a transversal T-gate, acts as a logical T-gate. But in this other code, actually it works as a multi-qubit control Z-gate. So it's a kind of cute example. Anyway, so let me just briefly show that this 15-qubit code has a T-gate as a good, a transversal logical gate. So first, we're going to label code words in the following way. Let me first define logical zero state. And in the discussion of the toric code, we have used this toric already, but oh, it's actually I even forgot to define the stabilizers. That's horrible. Yes. Yes, stabilizers in this code is X operator on volume and Z operator on phase. And then all the volume operator has 8 body. And then phase operator has 4 body. Now, there are 4 volume operators on color A, color B, color C, and color D. So this is this 8-body X operators. So what it means that we start from this trivial product state and we apply this operator. This is a projector. Yes, and this is a projector. And so in the discussion on toric code, I think discussed that if we do this construction, this is a code word. That is because yes. Anyhow, this is the code word. And then you can define the code word for 1 by just doing Now, what is T-gate? T-gate is gate which implements I square root on state 1. So if we apply T gate 15 times on logical 0 state, like everywhere, then what it would do is, well, this is a bunch of combination of 0 state and 1 state and their combinations. So this is some like 0, 1, so on, these kind of binary strings. What we get is that right, so we can think about computational basis state, 0, 1, 0, 1 state. If we apply the T gate, then it does not change the basis state, but adds some phase. And the phase factor is related to the weight of this binary string. Weight means that you just add up all of them. So that is because whenever you find one state, you multiply by square root I. This is the case. But one crucial observation is that these are 8-body operators, and well, for 8-body operators, it adapts to multiplies to 1. And it turns out any combination of these operators gives you a number 8. So it turns out this is the case. Okay. But if I look at this object, it's a logical 1 state. And now 1 and 0 are sort of flipped, which means that this is, most of them are either 7-body or 15-body. So this means that the result will be the 7, which is actually right. So this implies that this T is logical T minus 1, T Dagger gate. So this is how you can sort of see this statement. So it's important that you sort of start from this easy code word state. You can construct from product state and then count the number of non-zero weight of the non-zero elements, counting the weights and so on. Yes?
So where is the asymmetry between the X operator and the Z?
Oh, yes.
Where does this stem from?
Where does it stem from? Yeah, well, right. Where? It's a it's a very, very tricky question to ask, so to answer, and it turns out that right. So maybe one comment is I can think about 4D color code, 5D color code, 6D color code, and so on. And then X operator, we always put it in the D-dimensional object. So in 4D, you put it in the 4D volume, but we always put Z on the face. And then that's how we can construct the model. So this construction is really asymmetric. And then because of this asymmetry, if you look at the size of a logical X and logical Z operator, I forgot which of them is small. I think, yes, x of logical x must be bigger, I think. Yes, logical x must be bigger and the logical z is smaller. So for z error, it's weaker. X error, it's strong. So there is a bias.
It's a construction on purpose.
But
how come we don't, like with the 2D color codes, we don't have like symmetry?
Right.
It's just a different construction of a code.
It's just a different construction, and it has a different purpose in the sense that the 2D color code is completely symmetric. So for this reason, you can implement any Clifford gate permitting Pauli operators. You can implement any Clifford gate transversally. But in this case, 15-qubit code, you can implement this so-called T-gate. And T-gate is not something you exchange Pauli operators. And it has some asymmetric structure. So now let's suppose that this 3D color code somehow has this XZ symmetric structure and T-gate. Then it would imply that I can do Clifford plus T, which means that I can do universal transversal gates. But this is prohibited in the sense that there is a no-go theorem. You cannot do all the transversal gate in a single code. So in some sense, if we are looking at this T gate and so on, then you need some asymmetry. And then because of this asymmetry, you have X and Z, and the code is a bit weak against one type of the error. Yes?
Isn't it the case that all odd-dimensional toric codes have some kind of asymmetry?
That's actually related, although yes.
That was my understanding as the reason why you have the symmetric and the 2D coordinate is because it's an even number. Presumably a similar thing in whatever four-dimensional coordinates you write down.
Right.
But you have to transform in even dimensions that swaps the labels, but I'm not sure you can do this with your X ops on the faces and the Z ops on the bodies.
Right. So what you're saying is correct, except one sort of a caveat is that in 4D toric code, you can think about the dual construction where X and Z are sort of not asymmetric, and then it has a plain like logical operator X and Z. But you can think about 4D toric code with a string and a 3-dimensional logical operator too.
That's why I used the plural, so I understand it. There's more than one way of doing.
So right. So actually I was not precise at all. So when I say D copies of D-dimensional toric code, I'm mentioning this particularly asymmetric one.
So color codes generically asymmetric like this?
Above 2, yes.
Right, so when you decompose them into toric codes, do you have to choose an asymmetric toric code? Right, so you have to avoid the ones that are symmetric.
Right, well, I was not planning to go into technical details, but as I said, in this example, I pick X on volume and Z on face, but in higher dimensions, X will be on D-dimensional volume and then Z will be on 2-dimensional volume. But you can change this dimensionality a little bit. So D minus 1 and the 3, D minus, I think that's how it works. Yes. And then these models will correspond to some toric code with some different choices of dimensionality of logical operators. So this correspondence holds for any choice of these operators. Any other questions? Yes.
I'm still confused about what do we mean by copies of D-dimensional?
Copies means really a copy in the sense that it's a non-interacting copy. So
it still encodes the same 1 qubit though.
Oh, so right. So this is the in the case of the torus. So you have a bunch of qubits, but by implementing this unitary operator, some short depth circuit, it turns out you can say like, okay, this qubit will be a qubit for toric code 1, this qubit will be a toric code 2, and then you completely separate them. So there's no entanglement between them. So that's what they mean by 2 copies of the toric code.
So like,
So it's just a tensor product of toric code. It's same as preparing two toric code and then sort of like make them overlap. That's.
I see, but if you have two toric codes, don't you have two qubits though?
Oh, right. But it's qubit, right? I mean, so what I'm saying is that you have this hexagonal lattice, then you can arrange this bunch of qubits saying like, you become a qubit for toric code 1, you become a qubit for toric code 2, and then you can just.
But what about counting the logical qubits?
Right, the logical qubit just seems like there's you have your 7 qubit code, you have one logical qubit, right?
7? Oh, right. Oh, so then that's another question. So this 2 copies, 3 copies is a statement without any boundaries. If you don't have any boundaries, you can just lift them and then decouple them together. But if you have a boundary, then, so let's say this 7 qubit code or this example, in the interior, on the bulk, you can sort of decouple 2 toric codes, but on the boundary, they are connected somehow nicely. And then, actually, in my paper with Alexander Kubica and Fernand Pastowski, we showed that so in the previous lecture, we discussed this rough and smooth boundary, but it's really like this. Then what we found is, where is the chalk? This one. Let's draw this line, and so you can imagine like origami or seed, and then fold it, then create some code which lives on this geometry, like triangle. Then this object is precisely this one. So this, actually, the color code with boundary is a folded toric code. But now I fold it, so it's like 2 sheets, like 2 independent sheets, right? So on the bulk, I see 2 copies of the toric code, but somehow they're coupled on this boundary. So in this case, C boundary. So A and B are trivial boundary with smooth and rough boundaries, but C somehow couples. So this question of boundary is pretty important in the sense that how you impose the boundary conditions, the action of the logical operators and so on, very crucial about choices of boundary. And also in the language of toric code, it is a question of how we choose the boundary conditions and how do we design the boundary with this nice anion condensation pictures and so on. So it's a very deep subject. Any other questions? Okay, so that is. Thank you very much.